Let's talk about one of the most maddening parts of modern life, your wireless connection. It's this invisible force that we all depend on, but it can feel totally random. The truth is, it's not random, it's just chaotic. Today, we're going to pull back the curtain on that chaos. You're going to see how engineers don't try to fight it, they actually lean into it, using some really powerful statistical models to build the reliable connections we can't live without. So let's dive in.
You know the feeling, right? You're deep into a movie, the connection is flawless, and then, boom, out of nowhere, that dreaded buffering wheel starts spinning. You haven't moved an inch, the router is sitting right where it always is, so what on earth just changed? Well, the answer is that the signal from your router to your device isn't just one clean, straight line. It's actually an incredibly complex, invisible web of signals that is changing every single millisecond.
So, to really get to the bottom of this, we're going to follow the exact path an engineer would. We'll kick things off with the invisible echoes that are bouncing all around us. Then, we'll look at how they model the simple fade in signal strength. After that, we'll dig into what happens when signals get smeared and why that's a huge problem. Then, we'll layer on the complexity of speed and space. And finally, we'll see how all these abstract models make their way right into your phone to give you that solid connection you expect.
Okay, our whole journey starts with a concept that's actually, believe it or not, pretty intuitive. We just have to stop picturing a radio signal as one little beam shooting through the air. It's a lot messier than that.
I want you to imagine you're standing in a huge canyon and you shout. The first thing you hear is the sound that traveled directly from your mouth to your ears, right? Almost instant. But then, a split second later, you start hearing all the echoes bouncing off the canyon walls. Some are loud, some are faint, some get back to you really fast, others take a little longer. A Wi-Fi signal does the exact same thing. There's one signal that goes straight to your device, but it also bounces off the walls, the ceiling, your furniture, even you, creating a whole mess of echoes.
And this whole jumble of echoes has a technical name, multipath propagation. So your phone or laptop isn't just getting one nice, clean signal. No way. It's getting a mashup of dozens, maybe even hundreds of copies of the original signal all arriving at the same time. And here's the kicker. Each one of those copies, or multipath components, has traveled a slightly different path. That means each one arrives with its own unique delay, its own strength, and its own phase. It's a real mess.
So how in the world do engineers make sense of this invisible chaos? They use this really elegant mathematical tool to take a sort of snapshot of it. It's called the channel impulse response. Think of it as a fingerprint of the wireless environment at one specific moment. This little function, C of tau and t, tracks two crucial things. First, there's tau, which represents the delay, how long each echo took to arrive. And second, there's t, which represents time itself, because this whole pattern of echoes is constantly shifting as things move. It's amazing, really. This one function can describe the entire wireless channel.
All right, let's build on that. We're going to look at our very first model, and we'll start with the simplest possible case. What happens when all those echoes we just talked about arrive at almost the exact same instant? In engineering terms, this is called the narrowband channel. So, in this narrowband world, the time difference between the first echo arriving and the last echo arriving is super, super tiny. It means all those echoes essentially just pile up on top of each other at your phone's antenna. Now, because each echo has a slightly different phase, think of them as little waves. They're going to interfere with each other. Sometimes their peaks line up and they add together, creating a really strong signal. That's constructive interference. But other times, a peak from one echo meets a trough from another, and they cancel each other out, creating a really weak signal. That's destructive interference. And this constant, rapid fluctuation in signal strength, that's what we call fading.
So you're probably thinking, how can you possibly predict this? It sounds completely random. Well, you can't predict the exact signal strength at any given microsecond. But, and this is the brilliant part, you can predict its overall statistical behavior. When you have a whole bunch of these random echoes, and no single one of them is way stronger than the others, you can use one of the most powerful tools in all of mathematics, the central limit theorem. It's a cornerstone of probability, and it basically says that when you add up a bunch of random things, the result isn't random noise. It actually follows a very specific, predictable pattern.
And when we apply that amazing theorem to our multipath problem, we get a famous model called Rayleigh fading. This is the go-to model for wireless signals in places like a dense city or inside a building, where there's no clear, direct line-of-sight path from the transmitter to you. And what this model tells us is kind of scary. Those moments where the signal gets incredibly weak, what we call a deep fade, they aren't rare accidents. No, they're a common, totally expected part of how the channel behaves.
So what does this statistical model actually tell us in the real world?
Well, one of its most critical predictions is that the signal you receive becomes essentially uncorrelated. Basically, it's a whole new random situation if you move just half a wavelength. Now, for the 2.4 gigahertz Wi-Fi you probably use, the wavelength is about 12.5 centimeters, so half of that is just over 6 centimeters. Think about that. Just by moving your phone the width of your hand, you can go from a spot with a perfect signal to a total dead zone, and then back to a perfect signal. It's also exactly why Wi-Fi routers have their antennas spaced apart. They're trying to make sure each antenna sees a different, independent version of the faded signal to improve reliability.
Okay, but remember, our first model was a simplification. We assumed all the echoes arrive at once. But what happens when they don't? What happens when they're actually spread out in time? This brings us to a much more complex and, frankly, more troublesome scenario that engineers call the wideband channel.
Let's really break down the difference here. In the narrowband case we just talked about, the big problem is that the signal strength just goes up and down, fading. But in this wideband case, the problem is totally different. Because the echoes are spread out over time, if you send a single, sharp pulse of energy, what arrives at the receiver isn't a sharp pulse, it's a stretched out, smeared out blob. And that smearing creates a whole new kind of distortion.
This smearing causes a huge problem called inter-symbol interference, or ISI. You see, digital communication is all about sending a super fast sequence of little data packets called symbols. With ISI, the energy from one symbol gets smeared out so much that it spills over into the time slot for the next symbol and it corrupts it. It's literally the radio version of slurring your words together. If it gets bad enough, the receiver has no idea where one symbol ends and the next one begins, and you just get a torrent of errors.
So to fight this ISI problem, engineers first have to measure it. They start by creating something called a power delay profile, which is basically just a graph that shows how strong the echoes are and when they arrive. From that graph, they calculate a single number called the RMS delay spread, which tells them, in a nutshell, just how smeared out the signal is going to be. Then, the inverse of that number gives them the coherence bandwidth. And this is the golden number. It tells an engineer the absolute maximum speed they can send data before ISI becomes a show-stopping problem that has to be dealt with.
All right, you still with me? Because now we're going to add two final layers of realism to our model. So far, we've kind of pretended everything is just sitting still. But in the real world, things move. And on top of that, modern devices use more than just one antenna.
We've all heard the Doppler effect, right? The sound of an ambulance siren gets higher pitched as it races towards you and then lower pitched as it moves away. Well, the exact same thing happens with radio waves. If you're walking around with your phone, or even if things are just moving in the room around you, it causes tiny shifts in the frequency of every single one of those multipath echoes. And what that means is the channel isn't just a static mess, it's a mess that's changing at a specific rate, and that rate is determined by speed.
And just like we had metrics for the smearing, we have metrics for this motion. The Doppler spread measures the range of all those little frequency shifts. So if you're in a fast-moving car, you're going to have a huge Doppler spread, and that tells an engineer the channel is changing incredibly quickly. The inverse of that is something called the coherence time, and this is absolutely crucial. It tells you for how long you can pretend the channel is frozen in time. All the complicated software in your phone that's trying to fix the signal has to work faster than the coherence time, or it can't keep up.
And finally, we add space to the mix. Modern systems, like Wi-Fi 6 and 5G, they don't just have one antenna, they have a bunch of them. The technology is called MIMO. Now, to make that work, the model can't just think about when the echoes arrive, it also has to consider the physical direction they're coming from, their angle of arrival. By understanding this spatial dimension, engineers can do some amazing tricks, like sending multiple, separate streams of data at the exact same time on the exact same frequency, which is a huge part of how we get those crazy fast speeds today. Okay, we have gone deep. We've talked about impulse responses, delay spreads, Doppler shifts, a lot of abstract stuff. So let's bring it all together. Let's see how all this complex statistical modeling actually helps design the phone that's sitting in your hand right now. This right here is the fundamental workflow of a wireless engineer. First, they go out and they characterize real-world places. They literally take measurements in a downtown city block, or an open-plan office, or a suburban house. Second, they take that data and model it. They fit it to a statistical model, like Rayleigh fading, and they figure out the key numbers, like the delay spread and the Doppler spread. Third, they simulate. Long before a single piece of hardware is built, they use these models to test how a new technology will perform, predicting its speeds and how many errors it will have. And finally, based on all that, they design.
The simulations tell them exactly what problems to expect so they can build the solutions, like special equalizers to fight ISI or clever antenna techniques to beat fading, right into the system from day one.
And that really is the whole point of this. That moment your video buffers, it isn't a sign that Wi-Fi is broken. It's just a tiny glimpse of the unbelievable statistical chaos that's happening all around you all the time. The fact that it works at all, let alone at the gigabit per second speeds we see today, is an absolute miracle of engineering. Engineers didn't try to eliminate the chaos. They learned to understand it, to model it, and then to design systems that are so clever they can not only survive in that chaos, but actually thrive in it.
And that really leads to a fascinating final question. We have become incredibly good at modeling and predicting the behavior of this invisible world. So, what's next? Will future systems use AI to predict the channel's behavior from 1 millisecond to the next with near-perfect accuracy? Or, even crazier, will we develop things like smart surfaces on walls that can actually control the reflections, basically sculpting the multipath environment to create a perfect, custom-made channel on demand? The journey from modeling chaos to actually controlling it, that might just be the next great leap in wireless.
If you enjoyed this deep dive into the invisible world of wireless signals and you want more explainers like this, definitely subscribe to the channel. Please give this video a like and let us know what you think in the comments. We'd love to hear any questions you have or any other complex topics you'd like us to break down next. Thanks so much for watching.